All right, we're now going to turn our attention to classifying all simple extensions algebraically. So algebraically means in terms of quotients of polynomials and or rational functions and or polynomial rings. Okay, so our first theorem is that, so remember there's two types of simple extensions. There's transcendental and there's algebraic. So we're going to deal with the easy one first. The easy one's actually transcendental. It's the transcendental is easy algebraically because there's no like relations whatsoever. You just sort of add in an element that essentially functions as t. So if you have a transcendental extension, k adjoin alpha over k. So some examples might be like q adjoin pi over q, right? That's an example. Then it's isomorphic over k. Over k just means it's the identity on k, which I emphasize here, to rational functions over k. And the isomorphism is evaluated at alpha. So you should think about this as evaluate at alpha. Right? So I might even call this ev sub alpha for evaluated alpha. All right, proof. Well, define. Well, I'm just going to call it evaluated alpha because that's what I've done here. The book uses phi, but it's better to be more descriptive than less descriptive, in my opinion. And we're going to define it by, well, if we have a quotient of polynomials, f over g, we're going to plug in alpha. Great. Let's just notice some things here. If g is not 0, then when we plug in alpha, we don't get 0, as alpha is transcendental. It satisfies no polynomial equation. So you can never plug it into a polynomial, a non-zero polynomial, and get 0. So evaluation at alpha is well defined as a function. And we just need to check that it is a homomorphism and it's onto. But what's going to be the check that it's a homomorphism? We have to show that addition before evaluation and addition after evaluation are the same. Well, I'll do the multiplicative one, and then we can agree that the addition is the same. So to check homomorphism, what would happen? Well, we do multiplication first because I said, because I don't want to do common denominator stuff. All right, so this is evaluate before, or so this is multiply before, then evaluate, and this is evaluate after. Okay, so let's multiply these out on the left, and then we're going to plug in alpha. Just give myself a little more space here. And then on the right-hand side, we're going to plug in alpha and then multiply. All right, cool. On the left-hand side, we plug in alpha. And on the right-hand side, we multiply. As you can see, there's absolutely no difference. There's no difference because why would there be a difference? You know, it's transcendental. So when we deal with the rational expressions or rational functions, the arithmetic's exactly the same. So addition is exactly the same too. Addition is going to work out. I'll put a check mark here. And then lastly, well, that's it actually, just addition and multiplication. Okay. Now, is every rational expression, does it come from plugging in something into a rational function? Certainly it does. So this is also clearly onto as well. Thus, evaluation at alpha is an isomorphism. And so that's the end, right? It's the end. Not only did we actually show that all simple transcendental extensions are the same in quotes, the same in our class means isomorphic, to the field of rational functions, but we did better. We have an explicit way of relating the two. So as an example real quick, suppose I wanted you to show Blue. Choose blue. Suppose I wanted you to show, let's say Q adjoin pi over Q is isomorphic to Q adjoin E over Q. This is going to be one of the most helpful tricks that you will learn in the class, and it's not super important in this transcendental case, but we're going to do it again in the algebraic example, and it's going to be incredibly helpful. But what can we do? Well, I know that Q adjoin T is isomorphic to Q adjoin E via evaluate T at E, right? I'll just say Ev sub T equals E because we have more than one thing to evaluate at. I also know that Q adjoin T is isomorphic to Q adjoin pi via Ev sub T equals pi. Now, isomorphisms all have inverses. The inverse of an isomorphism is again an isomorphism. So what we can do is if we want an arrow from Q adjoin pi to Q adjoin E, we can undo this one. And then we can follow that by doing evaluate T at E. So the isomorphism from Q adjoin pi to Q adjoin E is given by the composite. You first undo evaluating T at pi, and then you evaluate T at E. Now this has a very simple interpretation. This is something we saw, I think, in chapter 1. This is just replace pi with E. That's all it is. But this sort of way of passing from numbers to the field of rational functions, or later it's going to be quotients of polynomials. This is incredibly helpful. This way of undoing an isomorphism and then following it with an isomorphism. We're going to see this again very shortly.